module, we will be studying about electrostatic potential energy. The coulombs, or the electric force F between charges Q1 and Q2, separated by a distance d, is expressed as K into Q1 Q2 by d square, where K is the constant, which is equal to 1 by 4 epsilon naught. We can say that the electrostatic force F is inversely proportional to the square of the distance d between the charges. It is also important to note that the electrostatic force between two charges at rest, expressed by Coulomb's law, is a conservative force. When a force acting between two bodies is inversely proportional to the square of the distance between them, that force is said to be obeying the inverse square law. We observe that electrostatic force obeys the inverse square law. We know that work done against electrostatic force is known as electrostatic potential energy in a charged particle in an electric field. Let us now discuss the electrostatic potential energy of a charged particle in an electric field. Consider the electric field of a positive charge Q placed at the origin, or let Q naught be a positive charge located at point A. To bring the charge Q naught from point A to a point B closer to charge Q, some work has to be done against the force due to the electrostatic field Fa. The external force F required to move Q naught should be just about sufficient to overcome the electrostatic repulsive force Fe on Q naught. Therefore, we can say that the magnitude of the external force F is equal to the magnitude of Fe. Let us label it as equation 1. The external force F should not give the charge Q naught any acceleration. The net force on Q naught must be 0. The charge Q naught must be brought from point A to point B at a very low constant speed. The work done to move Q naught from point A to point B is denoted by WAB and is told as electrostatic potential energy for charge Q naught. If we remove the external force F, then the charged Q naught moves away from Q in the direction of the electric field and gains kinetic energy such that the gain in kinetic energy is equal to the loss in an electrostatic potential energy. Sum of the kinetic and electrostatic potential energies of charge Q naught is always a constant or conserved. We know that the work done by the external force F to move charge Q naught from point A to B is denoted by WAB. This is equal to the integral of external force F dot dr in the limits A to B, where dr is the distance between the 2 points. Let us label it as equation 2. From equation 1, we know that the magnitude of the external force F is equal to the magnitude of force Fe due to the electric field. But the direction of the electrostatic force of Fe is opposite to that of the external force F. Therefore, we can say that external force F is equal to minus Fe. Let us label it as equation 3. Substituting the values of the external force F from equation 3 in equation 2, we get WAB is equal to minus integral Fe dot dr in the limits A to B. Let us label it as equation 4. In equation 4, The work done against the electrostatic force is told as electrostatic potential energy. Hence, at every point of the electric field, the charge Q0 possesses electrostatic potential energy. Let the potential energy of the charge Q0 at point A and B be UA and UB respectively. The work done by the external force F, as given by equation 4, is also equal to the difference in the electrostatic potential energies of the charge Q0 at the points A and B in the electric field. Let us label it as equation 5. The work done by the external force F is WAB is equal to delta U. Let us label it as equation 6. From equation 5 and 6, the work done by the external force WAB can be rewritten as delta U is equal to UB minus UA. Let this be equation 7. The difference in electrostatic potential energy between 2 points in the electric field of any arbitrary charge distribution will be equal to the work done to move a charge from one point to another. The work done according to equation 7 is independent of the path followed to move Q0 from A to B without accelerating Q0, and is dependent only on the initial and final position. Hence, the electrostatic force Fe is a conservative force, and the work done against the electrostatic force Fe is independent of the path followed. Adding a constant C to the electrostatic potential energy at point A and B will not alter the values of the difference in electrostatic potential energy between the charges and work done at WAB. Hence, we can choose a convenient reference point where the value of potential energy is 0. Let point A at an infinite distance from the charge Q. The electrostatic potential energy of Q0 at point A is UA is equal to U. Infinity is 0. Therefore, the work done according to the equation 7 can be written as WAB is equal to UB minus U infinity, which can be written as WAB is equal to UB, since electrostatic potential energy at infinity is equal to 0. That is, U infinity is equal to 0. Let us label it as equation 8. Based on equation 8, the electrostatic potential energy of the charge Q0 can be defined as the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. We will be studying about the concept of electrostatic potential and potential due to point charge. In the earlier module, we have learned that the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. That is, the work done to bring the charge Q0 from point A at infinity to point B is equal to the potential energy of Q0 at point B. Since the force on charge Q0 due to any static charge configuration is F equal to Q0 E, the work done will be proportional to Q0. We can say that W is equal to a constant K into Q naught, or the quantity W by Q naught is equal to K. Therefore, the resultant quantity obtained is independent of Q naught. The work done per unit test charge is a characteristic of the electric field at that point due to the charge configuration and is known as the electric potential at that point in the electric field due to the charge configuration. The electric potential is denoted by V. Let us consider a point A between the origin and point B. Then, potential energy of the charge Q naught at points A and B is UA and UB respectively. We know that the work done by the external force to bring charge Q naught from point A to B is expressed as WAB is equal to delta U, which is equal to UB minus UA. If VB and VA denote the electric potentials at point B and A respectively, then the work done by the external force to bring the unit positive charge from A to B is equal to VB minus VA, which is in turn equal to UB minus UA by Q naught. Now, choosing A to be at infinity and also the electric potential at infinity as 0, the work done by the external force to bring the unit positive charge from infinity to point B in the electric field is equal to the electric potential VB at point B. The electric potential V at any point in the electric field of a charge configuration is equal to the work done to bring a unit positive charge from infinity to that point in the electric field. Let us obtain an expression for the electric potential V at a point in the electric field of a point charge Q at the origin using the definition of the electric potential V at a point in the electric field of a static charge configuration. Consider the electric field of charge Q, in which B is a point at distance r from it. Consider the point A in the electric field, which is at distance r dash from the charge Q. Let a unit positive charge Q naught with a charge of +1 coulomb be placed at point A. The electrostatic force Fe between Q and a unit positive charge placed at A will be equal to 1 by 4 pi epsilon naught into Q into 1 by r dash square into r dash cap, where r dash cap is the unit vector along the direction of OA. Therefore, Fe will be equal to 1 by 4 pi epsilon naught into Q by r dash square into r dash cap. Let us label it as equation 1. Now, let us move the unit positive charge from A towards B in the electric field by a small distance dr dash, and let dW be the work done in the process. The external force F required to move the unit positive charge is equal and opposite to the electrostatic force Fe. dW will be equal to F dot dr dash. Let us label it as equation 2. We observe from equation 2 that the value of dW is negative since charge Q naught is moved against the direction of the electric field. Now, let us assume that the unit positive charge is brought from infinity to point B in the electric field, and let work W be done for this process. Then, W is equal to the integral dW. Let us label it as equation 3. Substituting the value of dW, we get W is equal to minus integral 1 by 4 pi epsilon naught Q by R dash square into dr dash in the limits ranging from infinity to R. Let us label it as equation 4. Since 1 by 4 pi epsilon naught Q are constants and evaluating only the integral, we have integral 1 by R dash square dr dash in the limits infinity to R is equal to minus 1 by R dash in the limits infinity to R, which is equal to 1 by R minus 1 by infinity. On further simplifying, we get W is equal to 1 by 4 pi epsilon naught Q by R. Let us label it as equation 5. This is the expression for work done to bring a unit positive charge from infinity to R, which is equal to the electric potential V at point B. Therefore, the electric potential V at point P is equal to 1 by 4 pi epsilon naught Q by R, which is the expression for electric potential at P in the electric field of the point charge Q. Let us label it as equation 6. The electric potential V is a scalar quantity and its SI unit is joule per coulomb or volt. 1 joule per coulomb is equal to 1 volt. We know that the electric field E of a point charge Q at a distance r from it is inversely proportional to the square of distance r from it. Here you can see a graph showing the variation of electric field E with respect to r. The electric potential V at a point in the electric field of a point charge is inversely proportional to the distance r from the charge as seen earlier. The graph shows the variation of the electric potential V with respect to distance r from the charge. It is important to note that the electric potential V at a point in the electric field can be positive or negative. In this module, we will be learning about the potential energy in the external field. We know that electrostatic potential energy U for a system of 3 charges Q1, Q2 and Q3 can be calculated using the formula U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2, R23 is the separation between Q2 and Q3, and R13 is the separation between Q1 and Q3 respectively. Let us label it as equation 1. Equation 1 can also be written as U is equal to U12 plus U23 plus U13. Let us label it as equation 2. In equation 2, U12, U23 and U13 are the electrostatic potential energies for the pair of the charges Q1 Q2, Q2 Q3 and Q1 Q3 respectively. Let us now derive an expression for the electrostatic potential energy of the system of charges in terms of the potentials. Let V be the potential at point A1 in the electric field A, produced by a source charge. Here, R1 is the position vector of the point with respect to the origin. Let us consider the charge Q1 at infinity from point A1. If W1 is the work done to bring the charge Q1 from infinity to the point A1 in the external field, then the external electric potential at the point A1 is V of power 1 equal to W1 by Q1. This implies that W1 equal to Q1 into V of power 1. Here, we assume that the potential due to the source charge at infinity is 0. This implies that V of power 1 is also the potential difference between the point and infinity, which is delta V. Now, if Q1 is released at point A1, it moves away in the direction of the electric field to infinity and gains kinetic energy equal to W1 when it reaches infinity. If V of power 1 is plus 1 volt, then the potential difference between the point A1 and infinity is delta V is equal to V of power 1 minus V infinity, which is equal to plus 1 volt. Now, if Q0 is an electron which is at rest at infinity, is released under the potential difference, then it moves towards the point A1. Since A1 is at a higher potential compared to point at infinity, the electrons gain kinetic energy, which is equal to Q0 into V of power 1. The magnitude of the charge on the electron is 1 into 6 into 10 power minus 19 coulomb, and V of power 1 is equal to 1 volt. Therefore, the kinetic energy gained will be equal to 1.6 into 10 power minus 19 joule. This kinetic energy gained by the electron is called 1 electron volt. Electron volt is defined as the kinetic energy gained by an electron when accelerated under a potential difference of 1 volt. We have seen that the work done to bring a charge Q1 from infinity to point A1 is given by W1 is equal to Q1 into V of power 1. Now let us consider another point A2 in the electric field, whose position vector with respect to the origin is power 2, and the external potential at the point is V of power 2. Let the distance between points A1 and A2 be R12. Let us bring another charge Q2 from infinity to the point A2 in the electric field, and let the work done in this process be W2. Hence, work done to move the charge Q2 from infinity to the point A2 is Q2 into V of power 2. If Q2 is now released, it moves due to electric field E and also due to the electric field of Q1. Work has to be done to hold the charge Q2 against the force due to the electric field A and also due to that of Q1. Work done to hold Q2 against the electric field due to Q1 is expressed as W12, which is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12. The total work done to hold Q2 at rest at A2 is Q2 into V of R2 plus W12. Substituting the relation for W12, we have total work done is equal to Q2 into V of power 2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. The total work done to assemble the system of charges in the external electric field is equal to Q1 into V of power 1 plus Q2 into V of power 2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R12, which is the electrostatic potential energy in the system of charges. We will be studying about capacitors and capacitance. Capacitors are devices that store electric charge. A capacitor essentially consists of a system of two conductors close to each other and separated by an insulating medium. The conductors can be of any arbitrary shape. By connecting them to the two terminals of a battery, the conductors are given equal and opposite charge of magnitude Q. The conductors carrying the charge are referred to as the plates, and because the plates are charged, an electric field of strength E exists between the plates. The potential due to the plate having excess positive charge plus Q on it is V1. The potential due to the plate having excess negative charge minus Q on it is V2. The positively charged plate is at a higher potential than the negatively charged plate. Therefore, V1 is greater than V2. Hence, the potential difference exists between the two plates. Let the potential difference between the plates be V is equal to V1 minus V2. As potential difference is measured in volt, this potential difference is referred to as voltage. We see that the total charge on the capacitor is plus Q plus minus Q equal to 0. As the conductors have charges of equal and opposite magnitude, it is a common practice to refer to the magnitude of charge on the conductors as the charge on the capacitor equal to Q, and the potential difference between the plates of the capacitor as the potential of the capacitor V. The electric field strength in the region between the plates increases as the magnitude of the charge on each plate of the capacitor increases. Then, the potential difference between the plates also increases. Since the potential difference V between the plates increases linearly with the charge on the capacitor, Q and V are proportional. Hence, the ratio Q by V is equal to C, where C is a constant, which is the capacitance of the capacitor concerned. It is important to note that the capacitance C of a capacitor is its ability to store electric charge. Greater the capacitance C of a capacitor, greater is the charge it can store, and hence, greater is the electrostatic potential energy. The capacitance C depends on the size, shape, the medium between the plates, distance between the plates, and also the SI unit for capacitance C is the ratio of SI unit of charge to SI unit of potential difference, which is Coulomb per volt. It is also referred to as Farad, named after the English physicist Michael Faraday. In practical application, we use submultiple units of capacitance like microfarad, nanofarad, and picofarad, as farad is a measure of higher magnitude. So, we will study about parallel plate capacitor. Let us first understand the structure of a parallel plate capacitor. A parallel plate capacitor consists of two metal plates, each of area A and separated by a distance d. When the plates of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q, and the other is given an excess charge minus Q. As a result, a uniform electric field is created between the plates of the capacitors. Towards the edges of the plates, we observe fringing in the electrical field. That is, the field is non-uniform when the plates of the capacitor are separated by some distance. We know that d is the distance between the plates. But if d square is very less compared to the value of the area A, the fringing effects can be neglected in the regions which are far off from the edges of the plates. Let the magnitude of the charged density be sigma for the plates with the charge q on them. Then sigma is equal to q by A. Let us label this as equation 1. Let us assume the region on the left side of the capacitor as region 1, region between the plates as region 2, and the region on the right side of the capacitor as region 3. Let us now calculate the electric field in the regions 1, 2, and 3 with respect to the capacitor. We do this by applying the Gauss law to calculate the electric field in the regions 1, 2, and 3. We know that for a uniformly charged plane sheet of charge, the electric field strength E at some distance away from it is equal to sigma by 2 epsilon naught. Let us label this as equation 2. We use this result to calculate the net electric field strength in regions 1, 2, and 3. In region 1, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught and directed away from the positive plate and towards the left. We also see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught and directed towards the negative plate and towards the right. Hence, in region 1, the net electric field strength E naught is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electrical fields are oppositely directed. Now, let us look at the region 3. In the region 3, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught and directed away from the positive plate and towards the right. We see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught and directed towards the negative plate and towards the left. Hence, in the region 3, the net electric field strength is equal to plus sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electric fields are oppositely directed in region 3 as well. Now, let us look at region 2 between the plates of the capacitor. In region 2, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught and directed away from the positive plate and towards the right. We also see that due to the negative plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught and directed towards the negative plate and towards the right. The region 2, which is in between the plates, has two electrical fields of equal magnitude, sigma by 2 epsilon naught, which are both pointing towards the right. Hence, in the region 2, the net electric field strength E naught is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On simplification, we get E naught is equal to sigma by epsilon naught. Let us label this as equation 3. Let the potential difference between the positive and the negative plates P equal to V. For a uniform electric field of strength E between the plates of the capacitor, we have V is equal to E naught D. Let us label this as equation 4. Substituting equation 3 in 4, we get V is equal to sigma D by epsilon naught. But we know that the charge density sigma is equal to Q by A. Therefore, we have V is equal to QD by A epsilon naught. Let us label this as equation 5. Now, capacitance of a parallel plate capacitor C is equal to Q by V. Let us label this as equation 6. Substituting equation 5 in 6 and simplifying, we get capacitance C is equal to epsilon naught A by D. Let us label this as equation 7. It is important to note that this expression for the capacitance shows that the capacitance is directly proportional to the area of the plate A and inversely proportional to the distance between the plates. It is important to note that apart from the geometry of the plates, the distance between the plates, the capacitance of a capacitor also depends upon the dielectric medium between the plates. Let us try to examine this. When there is no medium between the plates, let the potential difference between the plates be V naught, the electric field strength be E naught, and let its capacitance be C naught. We know that the capacitance C naught is equal to Q by V naught. Let us label this as equation 8. The electric field strength E naught is equal to sigma by epsilon naught. Let us label this as equation 9. The capacitance C naught is equal to epsilon naught A by D. Let us label this as equation 10. After disconnecting the charging battery, let a dielectric medium fill the intervening space between the plates of the capacitor. Dielectric medium in between the plates will now be in the presence of the electric field in between the plates. We know that when a dielectric medium is in an external electric field, it is polarized. The net effect on the dielectric is that there is an induced positive charge density plus sigma dash on the right face and minus sigma dash on the left face. Due to this, there is a weak induced electric field, say E dash, in the direction opposite to that of E naught. Since the dielectric material has lesser number of free charge carriers as compared to the metal plates, which are conductors. Then, according to Gauss' law, the electric field strength E in the dielectric will be E is equal to sigma minus sigma dash by epsilon naught, which is less than the magnitude of E naught. The potential difference between the plates V is equal to ED, which now becomes V is equal to sigma minus sigma dash into D by epsilon naught, and hence V is less than V naught. In the case of linear dielectrics, sigma dash will be proportional to the external electric field strength E naught. But since E naught is equal to sigma by epsilon naught, it applies that the value of sigma minus sigma dash is proportional to the sigma value. Or we can say that the sigma minus sigma dash is equal to sigma by K, where K is a constant of proportionality, which is called the dielectric constant of the medium. Since the electric field strength E is less than E naught, and hence potential difference V is less than V naught, this clearly implies that the value of K must be greater than 1. For any dielectric medium other than air, K is greater than 1. Using sigma minus sigma dash equal to sigma by K in the expression for V, we get V is equal to sigma d by k epsilon naught. But since sigma is equal to Q by A, we have V is equal to Qd by A, k epsilon naught. Therefore, the capacitance with a dielectric medium is C dash equal to Q by V. Here, it is of importance to note that since the charging battery is disconnected, the charge on the capacitor remains constant even after the introduction of the dielectric. Now, substituting value of V in the expression for C dash and simplifying, we get C dash is equal to K epsilon naught A by D. Here, the value of K epsilon naught is called epsilon, where epsilon is called permittivity of the medium. For air, the dielectric constant K is equal to 1. Hence, we have epsilon equal to epsilon naught for air. For dielectrics other than air, we have the dielectric constant K greater than 1. The dielectric constant K of the medium is defined as the ratio of the permittivity of the medium epsilon to the permittivity of the free space epsilon naught. We know that C naught is equal to epsilon naught A by D. Hence, we can write C dash is equal to Kc naught. Since K is greater than 1 for any medium other than air, we have C dash greater than C naught. We can also write K as a ratio of C dash to C naught. Thus, the dielectric constant K is a dimensionless quantity and has no unit since it is the ratio between similar quantities. Dielectric constant is also called as the relative permittivity of the medium and is also denoted by epsilon r. K is also known as the factor by which the capacitance increases when a dielectric medium fills the intervening space between the plates of the capacitor. Therefore, we see that by introducing a dielectric medium between the plates of the capacitor, the capacitance of the parallel plate capacitor increases. We have learned earlier that a capacitor is an electric circuit element that is used to store charge temporarily. It in general consists of two metallic plates separated and insulated from each other by a dielectric medium. Capacitors having different values of capacitances are used in various power supplies. However, it is not always possible to obtain capacitors with the desired values of capacitances. In such cases, the desired value of capacitance can be obtained by a combination of capacitors in a series or a parallel combination of multiple capacitors. Let us first discuss about the series combination of capacitors. Consider two parallel plate capacitors A and B. The plates of A are labeled P and R, whereas the plates of B are labeled S and T. Let the capacitance of A be C1 and that of B be C2. The plate P of A is connected to the positive terminal of a battery, and the plate R of A is connected to the plate S of capacitor B. The plate T of B is connected to the negative terminal of the battery through a key K. This type of a combination of capacitors is called a series combination of capacitors. Let a potential difference, delta V, be applied across this combination by the battery. When the key is closed and the battery is connected to the combination of the capacitors, electrons are transferred out of the plate P of capacitor A and onto the plate T of capacitor B. Electrons are negatively charged and hence a negative charge is accumulated over the plate T. this charge be minus Q. Simultaneously, an equal amount of positive charge plus Q accumulates over the plate P. As minus Q accumulates on plate T, an equal amount of negative charge is forced off the plate S of the capacitor B. Hence, the plate S has an excess positive charge which is equal to plus Q. The negative charge, minus Q, leaving the plate S, travels through the connecting wire and accumulates on the plate R of capacitor A. Hence, the magnitude of charge accumulated on the plates of the capacitors connected in series is same. Let the potential difference across the capacitors A and B be delta V1 and delta V2 respectively. The relation between the capacitance of capacitors C, the charge Q accumulated on it, and the potential difference across its plates, delta V, is given by Q is equal to C delta V. Let us label this as equation 1. Following the same expression, we get Q is equal to C1 delta V1 for capacitor A and Q is equal to C2 delta V2 for capacitor B. Simplifying the two expressions, we get delta V1 is equal to Q by C1. Let us label this as equation 2. And delta V2 is equal to Q by C2. Let us label it as equation 3. In general, the total potential difference across any number of capacitors connected in series is the sum of the potential differences across the individual capacitors. Hence, the total potential difference offered by the battery delta V is equal to delta V1 plus delta V2. Let us label it as equation 4. Let Cs be the equivalent capacitance of the series combination of the capacitors. Then, we have charge Q is equal to Cs delta V. From this expression, we get delta V is equal to Q by Cs. Let us label it as equation 5. Substituting equation 5, equation 2 and equation 3 in equation 4, we get Q by Cs is equal to Q by C1 plus Q by C2. On simplifying the expression, we get 1 by Cs is equal to 1 by C1 plus 1 by C2. Let us label it as equation 6. The equation 6 gives the relation between the equivalent capacitance for the combination of the two capacitors connected in series and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in series. If n number of capacitors with capacitances C1, C2, C3, so on up to Cn are connected in series, then the expression for the equivalent capacitance of the combination Cs is given by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on plus 1 by Cn. Let us label it as equation 7. Hence, we can conclude that when a number of capacitors are connected in series, the reciprocal of the equivalent capacitance of the combination is equal to the sum of the reciprocals of the individual capacitances of the capacitors in the combination. Let us now discuss about capacitors connected in a parallel combination. Consider the two capacitors A and B connected to a battery that supplies a potential difference of delta V, such that the plates P and S are connected to the positive terminal of the battery, and the plates R and T are connected to the negative terminal of the battery through the key. Such a combination of capacitors is called a parallel combination of capacitors. When the key is closed, electrons transfer through the wire and reach the plates. This transfer leaves the plates P and S positively charged and the plates R and T negatively charged. The energy required for this transfer is taken from the battery. The chemical energy stored in the battery is converted to the electrostatic potential energy associated with the separation of charge across the capacitors. The flow of charge to the plates of the capacitors stops when the plates acquire the potential difference equal to that supplied by the battery. The charge acquired by the plates of the capacitors is the maximum when the potential difference across them becomes equal to that applied. Let Q1 and Q2 be the charge accumulated on the plates of the capacitors A and B, respectively. The total charge on the capacitors connected in parallel is equal to the sum of the charge on the individual capacitors. Hence, the total charge Q on both the capacitors A and B is equal to Q1 plus Q2. Let us label it as equation 8. As P and S are connected to the positive terminal of the battery, the potential at the plates is equal to the potential at the positive terminal of the battery. Similarly, the potential at the plates R and T is equal to the potential at the negative terminal of the battery. Hence, the potential differences across the capacitors connected in parallel are the same and equal to the potential difference applied across the combination. Following equation 1, we have Q1 is equal to C1 delta V. Let us label this as equation 9. And Q2 is equal to C2 delta V. Let us label this as equation 10. Let Cp be the equivalent capacitance of the parallel combination of the capacitors. Then we have Q is equal to Cp delta V. Let us label this as equation 11. Substituting equations 9, 10, and 11 in equation 8, and on simplifying, we get Cp is equal to C1 plus C2. Let us label this as equation 12. The equation 12 gives the relation between the equivalent capacitance for the combination of two capacitors connected in parallel and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in parallel. If n number of capacitors with capacitances C1, C2, C3 and so on up to Cn are connected in parallel, then the expressions for the equivalent capacitance of the combination Cp is given by Cp is equal to C1 plus C2 plus C3 and so on plus Cn. Let us label this as equation 13. So, we can conclude that when a number of capacitors are connected in parallel, the equivalent capacitance of the combination is equal to the sum of the individual capacitances of the capacitors in the combination. We will be studying about the Van de Graaff generator. Van de Graaff generator is a device that is used to build up very high voltages of a few million volts. This high voltage can build very strong electric fields, which can accelerate charged particles to very high speeds and high energy level. To understand the principle behind the working of a Van de Graaff generator, let us consider a large conducting shell of radius R1 with a charge plus Q1 on it. This charge is uniformly spread over the conducting shell. For such a charge conducting shell, we know that the electric field strength inside the shell is 0, and the electric potential V in the inside of the spherical shell has the same value at all the points inside the shell, and V is equal to 1 by 4 pi epsilon naught Q1 by R1. Let us label this as equation 1. We also know that the electric potential at the surface of the spherical shell is equal to the potential inside the shell. Let us assume that there is another smaller concentric sphere of radius R2 with a charge Q2 on it. Now, let us consider the potentials at the surfaces of the inner and the outer spheres. Let the potential at any point P on the surface of the inner sphere be VR2. This potential is due to the charge on both the spheres. Then, VR2 is equal to 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R2. Here, 1 by 4 pi epsilon naught Q1 by R1 is the potential due to the charge on the outer sphere, and 1 by 4 pi epsilon naught Q2 by R2 is the potential due to the charge on the inner sphere. The potential at any point S on the surface of the outer sphere is VR1. This potential is due to the charge on both the outer sphere as well as the charge on the inner sphere. Here, V of R1 is equal to 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R1. Here, 1 by 4 pi epsilon naught Q1 by R1 is the potential due to the charge on the outer sphere, and 1 by 4 pi epsilon naught Q2 by R1 is the potential due to the charge on the inner sphere. The potential difference between the inner and outer spheres is delta V equal to VR2 minus VR1. Substituting the values of VR2 and VR1 in the expression for delta V and simplifying, we get delta V is equal to 1 by 4 pi epsilon naught Q2 into 1 by R2 minus 1 by R1. We see that the potential difference delta V depends on the value of Q2. Since Q2 is positive, the value of delta V is also positive. This clearly implies that the potential at the inner sphere is greater than the potential at the outer sphere. From the expression for delta V, we also see that the potential difference between the inner and outer spheres is independent of the charge Q1 given to the outer sphere. If we now connect the inner sphere to the outer sphere, charge flows from the inner sphere to the outer sphere, since the inner sphere is at a greater potential as compared to the outer sphere. Therefore, we can keep on adding charge to the outer sphere by supplying charge to the inner sphere, as it flows from the inner sphere to the outer sphere. Therefore, the potential at the outer sphere keeps on rising till it reaches the breakdown field strength of air, when it starts leaking off to the air. Due to the small charged sphere, which is within the large sphere, we can keep piling up larger and larger amount of charge on the latter. This is the principle of the Van de Graaff generator. Let us now look at the kinetic diagram of the Van de Graaff generator. It consists of a hollow metallic conductor P, which is mounted on the insulating column. A pulley S is mounted at the center of the sphere P. Another pulley T is mounted near the base of the conductor. And T can be continuously driven by an electric motor or by hand in case of the device being used for demonstration. A belt of an insulating material such as silk or rubber passes over the pulleys. As the pulleys move continuously, the belt also moves continuously. Two comb sheet conductors, X and Y, having metallic needles mounted near each of the pulleys, pointing towards the belt. The lower comb X is maintained at positive potential of about 10 power 4 volt by a power supply system. The upper comb Y is connected to the metallic sphere P. Because of the high electric field near the needles of the comb X, there is corona discharge and the air near it starts conducting. The negative charges in the air move towards the positively charged needles because of attraction. The positive charges in the air move towards the belt due to the repulsion and stick to the belt. The negative charges neutralize some of the positive charges on the comb X. The power supply keeps supplying more positive charge to the comb X, and effectively, the positive charge is transferred from the power supply to the belt. As the belt moves, this positive charge on the belt is carried up, and when it reaches near the upper comb Y, corona discharge occurs again, and the air starts conducting. Negative charges in the air move towards the belt, and the positive charges in the air move towards the needles of the comb Y. The negative charges neutralize the positive charges on the belt. The positive charges in the air, which have moved to the comb, are effectively transferred to the sphere P. Effectively, the positive charge on the belt is transferred to the sphere, and in a very short duration of time, the positive charge on the sphere moves to the outer surface and spreads uniformly. Thus, the device continuously transfers the positive charge to the sphere P, and hence its potential keeps on increasing. The potential builds up till the corresponding electric field reaches close to the breakdown field of air, which is of the order of 3 × 10 power 6 volt per meter. The limiting factor on the value of the potential of the sphere is the radius of the sphere. When the electric field outside the sphere P is just sufficient for dielectric breakdown of the surrounding air, no more charge can be transferred to the sphere P. A sphere of radius r equal to 1 meter can be raised to a potential of 3 × 10 power 6 volt by this method. The potential can be further increased by placing the sphere in a highly evacuated chamber, in which case there will not be any air surrounding the sphere.